Hello and welcome to video number 2 in acid-base equilibrium. Today we're going to talk about relative acid and base strengths. But first we're going to learn about amphoteric or amphiprotic substances. These are substances that can act as an acid or a base, depending on the reaction. So here we have an equation for the reaction of HSO3, hydrogen sulfite or bisulfite, and it's reacting with water. There it is, twice. 1, 2. And in one of them, this ion is going to act as an acid, and in the other, the ion is going to act as a base, which seems a little strange, but is totally possible. So first, let's link it with its conjugate acid-base pair. I'm going to find the sulfite ion. There it is. So it looks like hydrogen sulfite lost its hydrogen. It donated that hydrogen. It donated a proton. So in this case, it's an acid, making sulfite its conjugate base. In this case, if you link it with its pair, we have HSO3 minus goes to H2SO3. So in this case, it has gained a hydrogen. So this one started off as a base and produced its conjugate acid. And if you look at the waters will also switch. It'll go from being a base with a conjugate acid to an acid with a conjugate base. Both of them are amphoteric. Something else you want to be careful of is drawing the right arrow. We use a one-way arrow for strong acids and strong bases. We use a two-way arrow for weak acids and weak bases, because weak acids will only partially dissociate in water. In other words, some of the reactants are left over after the reaction has happened. In fact, the reaction just keeps going. Some of the products will go back and become reactants, and the reactants will continue going forwards and becoming products until it reaches equilibrium, where everything is happy and moving at the same rate. So make sure if you have a reaction that involves weak substances, you have a two-sided arrow. If it's dealing with strong substances, it's only one-sided because all of the reactants completely fall apart if they are strong. Okay, so now getting into the strengths. The stronger the acid is, the weaker its conjugate base. So for instance, we know HCl is a strong acid. So I'll end up with a whole bunch of hydrogens and a whole bunch of chlorides. And the HCl completely dissociates. It's gone. All of the hydrogens have released from all of the chlorides. And if you link up the conjugates, here we have our acid, and chloride would be our conjugate base. This chloride does not want to go back and become an acid. It has a negligible tendency to be protonated. It does not want to gain a proton, and so it basically isn't a base anymore. This equilibrium will lie really far to the right. A weak acid, however, only partially dissociates in an aqueous solution. So like, what's a weak acid? HF. We'll have hydrogen and our fluoride ion. So if we link up our conjugates and stuff with each other, here we have an acid, and here we have its conjugate base. And in this situation, since the acid was weak, its conjugate base it's also weak. However, it is relatively stronger. So let's see, this one, if you compare these two, this is very, very weak. I can spell weak, where this one is just weak. So the conjugate base of a weak acid is a weak base. However, in this case, the equilibrium will lie far to the left. Far to the left. And we'll go over this and how you can determine an equilibrium. So first, let's just summarize. The stronger the acid, the weaker its conjugate base. The stronger the base, the weaker its conjugate acid. Your equilibrium reaction will always be written in the direction favoring the ionization of the stronger acid and the stronger base. In other words, our reactants will always have the strong acid or the strong base, and our products will be their conjugates, which are very weak. So the strong stuff goes in the reactants, the weak stuff goes in the products. And here are some examples. We could write these out. We have HF goes to F. This guy is weak. It's weaker than this. So we'd actually have our fluoride ion in the reactants and our HF in our products. Here we know hydrochloric acid is very strong, so it would go in our reactants, and this would go in our products. All right, binary acid strength. So this is when you only have two elements. These rules are for when you only have two elements, like HF, HCl, HBr, and so on. So I'm just going to go ahead and write down what this looks like in the periodic table. Fluorine, chlorine, bromine, iodine. This is our periodic table. And our acid strength will increase as you move down a group. Strong, weak. And this has to do with the size of the ion. And if you go down a group, you are increasing its ionic radius. And as you increase the ionic radius, the attractive forces diminish. And so on HI, our iodide is not holding on to that hydrogen with a whole lot of force, because that nucleus is so far away from that hydrogen, you're able to pull that hydrogen off very easily. It's easier to remove the hydrogen in a large compound. So here, HF, we know that fluorine is extremely, extremely small. So those protons are really close to that hydrogen, and it's holding on to that hydrogen. It does not want to lose it, and so it is harder to pull off that hydrogen, making it weak. And this one is strong. So we have, when we're dealing with just two elements, you're going to look at the radius. Okay, conjugate base strengths of binary acids. So it's the same exact thing, but now we're talking about their conjugate bases. So again, if you look at your periodic table with fluorine at the top and iodine at the bottom, these guys get larger. And as they get larger, the base strength gets weaker. Let's write that a little bit differently. I'll just say weak, strong. And we're talking about the conjugate bases. So that means that these would all be ions because they have lost their hydrogens from earlier. So these conjugate base strengths will decrease as you move down a group. Fluoride is a much stronger base, a much stronger conjugate base than iodide. Because the smaller the radius, the greater the ability to attract hydrogens, which is what bases do. Okay, well, what about oxyacids? When you have hydrogen, oxygen, and then something else. In this case, you have an acidic hydrogen attached to the oxygen, so HOY. So for instance, you could have hypochlorous acid, where you have hydrogen and oxygen attached to a chlorine, or you could have HYOA, where that A determines how many oxygens you have. So here's chloric acid. Acid strength will increase, when doesn't need to be on there, as the electronegativity of Y increases. So let's write these down. F compared to Cl compared to Br compared to I. So as you move down a group, you are decreasing the electronegativity, and as you decrease electronegativity, then you are, oh, hold on, let me reword that. Acid strength will increase as the electronegativity of Y, this piece on the end, increases. So for this, decreasing electronegativity in an oxyacid means weaker acid. This will be stronger relative to each other. So let's compare. We have some options here. You have HOCl compared to HOBr compared to HOI. So first let's figure out which of these is the most electronegative. In our list right now, chlorine is the most electronegative. And then we have bromine, which is in the middle. Whoops, I'm trying to do middle electronegative. And then iodine has the lowest electronegativity. So that means that chlorine is hogging all those electrons. It's pulling them all away from that hydrogen, and that oxygen is helping out, and that makes it easier to pop off this hydrogen. So the one that has the highest electronegativity is the strongest. So this is number 1. That's the strongest. Because our chlorine has the highest electronegativity, then it lowers a little bit, so HOBr, a little bit lower strength, and then here this is our weakest acid. Strongest to weakest acids. There you go. So as the electronegativity of your Y, this is Y, this is Y, this is Y, as the electronegativity of Y increases, it pulls those electrons further and further away from that hydrogen, and the acid strength increases because we're able to pull those hydrogens off much more easily. Okay, well, what if you have an oxyacid again, HOY, but this time we're going to increase the number of oxygens you have. Your acid strength will increase as more oxygens are added. By doing that, you are increasing the number of electronegative oxygen atoms, which again increases the electron density around Y. So we're pulling all the electrons over here around Y. If you look at the title, these are our electrons, and the more that we have them around Y, the less they are around H, which allows us to go boop, hydrogen's gone. So looking down here, I only have 1 oxygen. Here I have 2 oxygens, I have 3, and I have 4 around the Y. So as we add more and more oxygens, the acid strength increases. This is only true for your oxyacids, HOY. What about carboxylic acids? These are weak organic acids. Here is the carboxylic acid. So C double bonded to an O with an O and an H, and R can be anything. The more electronegative the elements that make up the R, the stronger the acid. So for R, as I increase its electronegativity, I will increase my acid, ooh, that's getting ugly, acid strength. The highly electronegative R group, whatever it is, it could be a group of things, the highly electronegative R group will pull the electron density away from the hydrogen. Same situation as before. The Y was pulling the electrons away from the hydrogen. Here the R is. That makes it easier to go boop and lose your hydrogen. So looking over here, we have CH3, a methyl group, versus CF3. What you're going to want to do is compare the electronegativities of these two guys. And in this case, if you were to look at hydrogen's electronegativity versus fluoride's electronegativity, this one is lower than this one. So all of our electrons are getting pulled that way, and our hydrogen gets knocked off more easily. Pretty cool. All right, so we're going to try predicting the position of proton transfer equilibrium. For the following proton transfer reactions, predict whether the equilibrium lies to the left or to the right. If it lies to the left, our value of K will be less than 1. That means that we will not have very many products, but we'll have a whole lot of reactants. If our value of K is, here, let's do that. If our value of K is greater than 1, it's lying to the right. That means we have a whole lot of products and not very many reactants. So let's look here. First, we're going to identify our conjugate acid-base pairs. So I have HSO4 and I have CO3 2 minus. So let's look for which one is going to lose its hydrogen. Looks like HSO4 is our lucky winner. It lost its hydrogen. So that must mean it's an acid, making SO4 its conjugate base, whereas our CO3 2 minus gains a hydrogen. So that means that this is our base and this is our conjugate acid. Okay, so let's look at the bases here. In our CO3 2 minus, we have carbon compared to sulfur, and if you look at them on the periodic table, our carbon is more electronegative than our sulfur, and in addition, it has less oxygens. It's got less oxygens on there, and we know the less oxygens we have, the less those electrons are pulled away from the hydrogen. And so this carbonate here is going to attract hydrogens more easily than the sulfate will, making carbonate stronger. So let me just back up a little bit here. Right now we're looking at our number of hydrogens. It had less hydrogens, so it's a weaker acid or a stronger base. They work in opposites because it has less oxygens. So since it is a stronger base, that means that it gets the proton, yay, which means that we are, let's see, we want to make sure that we write these reactions such that the stronger base is in the reactants. We want the stronger base to be in the reactants. And that means that it will be written exactly as it is, and it'll be moving, in this direction. Our base is the one that is gaining our hydrogens, and that means that we are going to be favoring the products. We're going to be making lots of products, and our K will be greater than 1. Let's try that one again. That could be a little confusing. So here we have HPO4 2 minus, hydrogens phosphate, and then we have water. Okay, let's look for our acid. It's going to be whatever loses hydrogens. There we go. Acid, conjugate, base. Those of you wanting to practice this concept, it's all over your homework worksheet, so just go there. So here's our acid and our conjugate base, and here is our base and our conjugate acid. So let's just compare the bases. Something that's important to remember is that hydroxide is the strongest possible base. So we don't have to do anything complicated here. It's strong. This is it. That's our strong guy. And we don't like to write our strongest base in the products. We want our strongest base to be in the reactants. So this would actually be written as H2PO4 minus plus OH minus reacts to form HPO4 2 minus plus H2O. But either way, we know that wherever our strongest base is, here I'm going to cross this off so it doesn't confuse us. If we were writing that reaction, we'd want to write the strongest base in the reactants. But in this situation, they didn't write it like that, and we know our strongest base is going to create a whole lot of its, in this case, acid, So it's going to create a whole lot of water. So in that case, our equilibrium is going to fall really far to the left. Now here, oh look, we have another hydroxide. This is our really, really strong base. So here I'll label, that's our base. This is our conjugate acid. Oops. This will be our acid and its conjugate base. So we know hydroxide is a really strong base. We also know ammonia is a really weak acid, which creates a pretty weak base. And in this case, our strong base is going to create a whole lot of its conjugate acid. So in this case, our equilibrium is going to lie to the right. So basically in these problems, you find your strong base, you draw an arrow pointing away from it, and in whatever direction the arrow is pointing, that's the way equilibrium will lie. Here's our strong base. Equilibrium will lie on the opposite side, on the left. In our previous example, this is our strong base. So our equilibrium is going to lie on the opposite side. It's going to lie on the right. Find the strong base. You'll know which way equilibrium lies. So here's just a chart of relative strengths of acids and bases. We have our hydrochloric acid moving all the way down to HClO3. Here we have our alkali metals, our calcium, our barium, our strontium with hydroxides. So these are our strongest. Our oxides are also pretty strong. Ammonia, however, not so strong. Okay, something that's important to know is water can act as an acid or as a base. We kind of touched on that earlier. Here we could link this hydrogen with this hydroxide, or we could link this hydrogen, did I say hydrogen? This water with this hydroxide, and this water with this hydronium. In one case, it donated hydrogen, so it went from an acid to, oops, I should use the same color. We have an acid and its conjugate base. Here we have a base and its conjugate acid. Now remember writing equilibrium expressions where we'd have K is equal to the concentration of our products over the concentration of our reactants with different exponents depending. We're doing the same thing here, Kw. We know that water is a liquid, or in this case it is. So we don't include liquids, we leave them out, which makes our equilibrium expression just hydronium concentration times hydroxide concentration. And so at 25 degrees C, we know that this equilibrium expression is always equal to 1.0 times 10 to the negative 14th. You are going to use this equation so many times, you will be repeating it in your sleep. So make sure you take note of it. So we could state that the concentration of hydronium times the concentration of hydroxide is equal to 1.0 times 10 to the negative 14th at 25 degrees C. The other way to write this is the concentration of hydrogen times hydroxide. Same thing. So this is super duper important. Trust me, you will use it a lot. Okay, so here are some equations, lots of exclamation points. They're important. You are going to use them. So we need to know that the concentration of the hydrogens released times the concentration of your hydroxides is equal to 1.0 times 10 to the negative 14th at 25 degrees C. We know in a reaction the pH plus the pOH is equal to 14. Something that you might have learned in the past is what pH actually means. pH is equal to the negative log of the concentration of hydrogen ions. And we know that you can solve for something inside of a log by taking whatever the log's base is. So in this case it's 10. If it doesn't say it's 10, I'm going to end up erasing this later. But I could do 10 to whatever the pH is and 10 to the negative log. Those go away. And I could solve for the concentration of my hydrogen ions. Sorry if you can hear that plane fly by. All right, and then the same thing happens with POH. POH is equal to the negative log of our hydroxide ions. The pKa plus the pKb is equal to 14. Ka is the equilibrium constant for our weak acids, and this one is for our weak bases. This is within an equation. So again, the pKa is the negative log of your, of Ka. And pKb is the negative log of your Kb. We also want to know that the pH is equal to the pKa plus the log of the conjugate over weak. Let's reword that. Let's see here. pH is equal to pKa plus the log of your A minus over HA. Whoops, that should be an H. So, and this is all in parentheses here. So if you had HA reacts to form H plus plus A minus, you would take the concentration of your conjugate acid over the concentration of your acid inside of the log. Another useful thing to know. And finally, if you take your equilibrium for your acid times the equilibrium for the base, you would always get 1.0 times 10 to the negative 14th. The next video is going to help you practice using these equations. Just know that they exist and be ready to use them. And finally, we'll end with a pretty little gradient that shows us our pH scale. Strongest base up here, bases. These are our acids. The strongest one is sodium hydroxide up here. Then we have our ammonia. Then we have our oceans. Oh, look at that. Our oceans are slightly basic. Pure water is basically neutral. Coffee is somewhat acidic. That's right, brush your teeth after you drink that coffee. Tomatoes are acidic. Vinegar, soda, very acidic. Lemon juice, oh my gosh, super acidic. And finally, hydrochloric acid, super duper acidic. All right, well, I hope that helped, and we will be practicing doing some calculations next time.